Synapsida is one of the two major clades of vertebrate animals in the group Amniota, the other being the Sauropsida, which includes reptiles and birds. The Synapsids were the dominant land animals in the late Paleozoic and early Mesozoic, but the only group that survived into the Cenozoic are mammals. Unlike other amniotes, synapsids have a single temporal fenestra, an opening low in the skull roof behind each eye orbit, leaving a bony arch beneath each. This accounts for their name. Casea represents one of the first large and highly successful herbivores among terrestrial synapsids. Among vertebrates, this feeding strategy can be subdivided into many categories, including folivory, frugivory, and granivory, but among early terrestrial vertebrates, it is feeding on leaves, stems, and roots. Herbivores use massive crushing dentition on the palate and mandibles. The locomotion of Casea involves a 3-vertebra sacrum in early synapsids and no apparent link to body size. Some argue that this sacral anatomy was related to more efficient terrestrial locomotion than to increased weight-bearing. Selective pressures for weight-bearing or more efficient locomotory styles and increasingly terrestrial lifestyles may have promoted the repeated acquisition of 3 sacral vertebrae in Synapsida. Edaphosaurus is known from at least 6 skulls associated with their lower jaws, as well as from the postcranial bones of several juvenile individuals. It has the typical casseed skull with a short snout tilted forward and very large external nares. However, it differs from other derived caseids by its postcranial skeleton with smaller proportions compared to the size of the skull. As with other advanced caseids, the teeth of Edaphosaurus were well suited for slicing and cutting vegetation. The presence of a highly developed hyoid apparatus indicates the presence of a massive and mobile tongue, which had to work in collaboration with the palatal teeth during swallowing. Despite looking like a big fat lizard, Caudelorhynchus was actually a very early synapsid, closer related to modern mammals than to reptiles, and it was a distant cousin of other stem mammals like the famous Dimetrodon. Around 3.5 meters long, it was one of the largest herbivores of the early Permian, with a very wide barrel-shaped body, chunky limbs, and a comically small head. It also had some surprisingly sizable nostril openings in that little skull, and it may have had a very good sense of smell or perhaps some sort of specialized breathing system like the modern Saiga's air conditioning nose. Although usually depicted as a fully terrestrial animal, the structure of Caudelorhynchus bones and its flattened paddle-like hands and feet have recently been used to suggest that it may have been semi-aquatic, more of a Permian hippo than a cow. But such a lifestyle would have required it to have a much more efficient method of breathing than previously thought, suggesting it had a mammal-like diaphragm, and possibly also explaining that weird nose. Laleutorhynchus is represented by a well-preserved postcranial skeleton, including 10 vertebrae, 15 ribs, a complete right scapulocoracoid and several foot bones. The specimen shows a mix of mature and immature characteristics, suggesting it was a late juvenile or young adult at the time of death. While the skull is unknown, it likely had a small size compared to the body, a triangular shape, and a forward-sloping snout with large external nostrils. Laleutorhynchus had a barrel-shaped rib cage, indicating a large digestive tract adapted for a diet of plants with low nutritional value. Histological analysis of rib bones suggests a spongy structure, thin cortex and absence of a distinct medullary cavity, indicating a possibly semi-aquatic lifestyle. However, the debate continues among paleontologists regarding the exact ecological niche of Laleutorhynchus, with some proposing a semi-aquatic lifestyle comparable to that of hippopotamuses, while others argue against it based on morphological and taphonomic evidence. The recently described Ascendonanus from the early Permian of Germany was a member of a group called Veranipids, which may have been an early branch of the synapsid lineage. Known from several near-complete fossils that include rare soft tissue impressions, it's the first varanopid to show preserved skin details, revealing a pattern of very lizard-like rectangular scales. It also had unusual mosaic-like patches of tiny osteoderms above its eyes, a feature previously known only in some temnospondyl amphibians. Whether this was the result of convergent evolution or the trait actually being ancestral to most tetrapods is unclear. Its slender body, long digits, and highly curved claws indicate it was an agile climber. It probably mainly lived up in the treetops, feeding on insects, making it one of the earliest known tetrapods specialized for an arboreal lifestyle. Archaeothrys was more advanced than the early sauropsids, having strong jaws that could open wider than those of the early reptiles. While its sharp teeth were all of the same size and shape, it did possess a pair of enlarged canines, suggesting that it was a carnivore. Its legs were articulated laterally at its pelvis and shoulders, which gave it a sprawling stance. The first toe is smaller than the second. Archaeothrys lived in what is now Nova Scotia, about 306 million years ago in the Carboniferous period. Nova Scotia at this time was a coal forest. The giant club mosses were very tall, some, such as Lepidodendron, up to 50 meters tall. Archaeothrys and the other early amniotes lived in the moist vegetation on the forest ground, together with the more terrestrially adapted labyrinthodont amphibians. Ophiacodon is believed to have primarily lived on land, although there have been debates among paleontologists about its potential semi-aquatic habits. Early proposals suggested an aquatic lifestyle based on features such as broad claws, thin jaws with small teeth adapted for fish consumption, and weakly developed bones resembling those of secondarily aquatic tetrapods. However, subsequent analysis has challenged these interpretations. For instance, broad claws are common among early tetrapods regardless of habitat, and the long hindlimbs of Ophiacodon would not have been effective for aquatic propulsion due to their small size and limited surface area. Examination of its vertebrae and femur suggests a predominantly terrestrial lifestyle, although the thick cortex of the femur leaves open the possibility of occasional amphibious behavior. Overall, current evidence indicates that it likely spent little time in water and was adapted for a terrestrial environment. Living during the late Carboniferous in Nova Scotia, the 70 cm long Echinopodon, a distant cousin to modern mammals, was previously known only from the fossilized remains of juveniles, with all known specimens showing slightly elongated spines on their vertebrae that gave it a sort of high-backed protosail appearance. A single vertebra identified as belonging to Echinopodon shows a much longer spine than anything we've ever seen before, and confirms that this species actually had a large elaborate true sailback, making it the earliest known tetrapod to experiment with this type of anatomy. This individual seems to have been older than the other known specimens, but still not fully grown, leaving the possibility that fully mature Echinopodon may have had even larger sails than this. The name Tetraceratops sounds like it should belong to some sort of large horned dinosaur. Actually, it was a small synapsid from the early Permian of Texas. Known only from a 9 cm long skull, it had 2 sets of saber teeth in its jaws and a total of 6 horns on its face instead of 4, 2 on its snout, 2 in front of its eyes, and 2 at the back of its jaws. It's unclear exactly what the rest of its body looked like, or even where it belongs in the synapsid family tree, but currently it's thought to be the earliest known member of the therapsids. The synapsids diversified rapidly following their first appearance in the geologic record, and 2 particular families developed large showy sailbacks completely independently of each other, the Edaphosaurs and the Sphenacodonts. Ianthosaurus here was a basal edaphosaur, known from the late Carboniferous of Kansas. It was smaller than many of its more famous relatives, only about 75 centimeters long, and seems to have been an insect-hunting predator. Its sail featured crossbars sticking out from the main spines on the front 2/3 or so of its body. The purpose of these extra ornaments is unclear, but they must have been useful for something because later edaphosaurs sported them much more extensively. Lupiosaurus was another edaphosaur, known from the early Permian of Texas. Only a few fragmentary fossils have been found, but it was probably an herbivorous species, 3 meters long, and seems to have had unusually beefy limbs. Unusually for an edaphosaur, its sail completely lacked the characteristic crossbars, which led to confusion over its classification when it was first discovered. With so much of its skeleton still unknown, however, it could still turn out to be even more unusual if other fossils are ever found. It was also originally named as Lupiosaurus, but was later changed when the first specimen turned out to actually be the pelvis of the amphibian Eryops, making the original name an invalid synonym. It was redescribed with new material with its current name, which was fortunate because the original name would have eventually had to be changed anyway due to it being preoccupied. Lupiosaurus was already assigned to a type of gecko. Edaphosaurids were a fairly early branch of the synapsids and were some of the earliest known tetrapods to develop into large specialized herbivores. Although their fossils are known from both North America and Europe, their European remains are very rare and fragmentary. Currently the best-known specimen is made up of a recently discovered partial spinal column and a few hand and tail bones. Given the name Remigiomontanus, this edaphosaurid lived in western Germany during the end of the Carboniferous and the start of the Permian. About 1.2 meters long, it seems to represent an intermediate form between small insectivorous or omnivorous edaphosaurids like Ianthosaurus and the huge herbivorous Edaphosaurus. Gordodon's sail spines were thicker than those of earlier species but still less heavy-set than those of later forms, and while each spine had numerous side projections, these structures were small, thorn-like and randomly distributed, unlike the more organized thick crossbars seen in Edaphosaurus. But its most distinctive features were its jaws and teeth. It had a narrow snout with a pair of large incisor-like teeth at the front of both its upper and lower jaws, followed by a large toothless gap and then a short row of small peg-like teeth. Overall, its tooth arrangement looked more like a modern herbivorous mammal than an early synapsid, much more highly specialized than anything else known to be alive at the time. The next synapsid known to convergently evolve similar teeth lived around 90 million years later. It probably had a very different diet to its relatives, with its specialized teeth and fairly slender body suggesting it may have been a selective feeder, cropping the softer, more nutritious parts of plants like the fleshy seeds and cones of gymnosperm plants. Its discovery also hints that herbivorous edaphosaurids in general were much more diverse than we previously thought, and there may be even more surprising forms out there still to be discovered. The sail along the back of Edaphosaurus was supported by hugely elongated neural spines from neck to lumbar region, connected by tissue in life. When compared with the sail of Dimetrodon, the vertebral spines are shorter and heavier, and bear numerous small crossbars. Edaphosaurus and other members evolved tall dorsal sails independently of sailback members of the Sphenacodontidae that lived at the same time, an unusual example of parallel evolution. The functions of the sail in both groups is still debated. Researchers have suggested that such sails could have provided camouflage, wind-powered sailing over water, anchoring for extra muscle support and rigidity for the backbone, protection against predator attacks, fat storage areas, body temperature control surfaces, or sexual display and species recognition. The height of the sail, curvature of the spines, and shape of the crossbars are distinct in each of the described species of Edaphosaurus and show a trend for larger and more elaborate projecting processes over time. A study comparing the microscopic bone histology of the vertebral centra of Edaphosaurus and Dimetrodon found that the plant-eating Edaphosaurus grew distinctly more slowly than the predator Dimetrodon, which had a higher growth rate, reflecting an elevated metabolism. Secodontosaurus is an extinct genus of pelycosaur synapsids that lived from between about 285 to 272 million years ago during the early Permian. Like the well-known Dimetrodon, Secodontosaurus is a carnivorous member of the Eupelycosauria family Sphenacodontidae and has a similar tall dorsal sail. However, its skull is long, low and narrow, with slender jaws that have teeth that are very similar in size and shape, unlike the shorter, deep skull of Dimetrodon, which has large, prominent canine-like teeth in front and smaller slicing teeth further back in its jaws. Its unusual long, narrow jaws suggest that Secodontosaurus may have been specialized for catching fish or for hunting prey that lived or hid in burrows or crevices. Although no complete skeletons are currently known, it likely ranged from about 2.7 meters in length, weighing up to 110 kilograms. Like the closely related Dimetrodon, Sphenacodon was a carnivorous member of the Eupelycosauria family Sphenacodontidae. However, it had a low crest along its back, formed from blade-like bones on its vertebrae instead of the tall dorsal sail found in Dimetrodon. Researchers currently recognize two species, Sphenacodon ferox and Sphenacodon ferocior. Ferocior can be up to 40% larger in overall size, at about 3 meters long, compared to Sphenacodon ferox, at about 2 meters. In addition, the dorsal spines in ferocior are proportionately 45% taller than in ferox. The recent discovery of a nearly complete skull of Sphenacodon ferox has helped clarify other distinctions between the two species, including the number of teeth in certain parts of the jaws and the size of the indented notch between the maxillary and premaxillary bones in the upper jaw. Tenospondylus were about 3 meters long. It was a carnivore and preyed upon animals close to its size. It had a long tail, short back spines, and a very deep yet narrow skull with massive jaws that had sharp teeth. Because of its large size, it was probably the apex predator in its environment, and might have competed with other predators like Dimetrodon for food. The spines of Tenospondylus are longer than those of Sphenacodon but shorter than those of Dimetrodon. They also lack the dumbbell-shaped upper profile of the latter genus and are more transversely flattened. The skull of Tenospondylus is, as far as can be judged from the limited material found, very similar to that of other Sphenacodontids. Dimetrodon is an extinct genus of non-mammalian synapsid of the early Permian period. With most species measuring 1.7 to 4.6 meters long and weighing 30 to 250 kilograms, the most prominent feature of Dimetrodon is the large neural spine sail on its back formed by elongated spines extending from the vertebrae. It was an obligate quadruped and had a tall, curved skull with large teeth of different sizes set along the jaws. Dimetrodon is often mistaken for a dinosaur or as a contemporary of dinosaurs in popular culture, but it became extinct some 40 million years before the advent of dinosaurs. Although reptile-like in appearance and physiology, Dimetrodon is much more closely related to mammals than to reptiles, though it is not a direct ancestor of mammals. It was probably one of the apex predators of the Caesuralian ecosystems, feeding on fish and tetrapods. Smaller Dimetrodon species may have had different ecological roles. The sail of Dimetrodon may have been used to stabilize its spine or to heat and cool its body as a form of thermoregulation. Some recent studies argue that the sail would have been ineffective at removing heat from the body, due to large species being discovered with small sails and small species being discovered with large sails, essentially ruling out heat regulation as its main purpose.